I got interested in quantum because the next era in human technological evolution is not going to be artificial intelligence, it will be quantum applications. So you see these sort of, it's usually hardware inventions that give you these fantastic jumps in human interaction and overall economic productivity and performance. So while artificial intelligence is exciting, it's really interesting, my perspective, and again, all of this is my opinion, is that with quantum, what you're going to see are a whole new set of problems that can be solved that we could not solve before, whether these are problems we currently imagine, or once the technology comes about, these are problems we will discover that we can solve. We didn't even know that they were problems that existed, much like much of human history. So roughly divided, canonically, when people try to sell quantum applications, they sort of talk about computing, cryptography, and sensing. And roughly, to kind of dive a little bit into them, for computing, there's, of course, breaking cryptography, so cracking your crypto codes for the internet. There's simulation of objects, for example, in chemistry. So huge potential applications in simulating protein folding and things like that. And you can do this without any mathematical simplifications or approximations. It gives you an exact simulation of how the experiment would run. Exciting for artificial intelligence, for dealing with high rank tensors, which give you emotional subtlety. So right now, chatbots are not too emotionally subtle, they're not too convincing. And recommendation engines, for example, in Netflix, they're, it's a bit gimmicky. We all feel that way. But with quantum technologies, you can really create something that would truly touch you and inspire you, and hopefully will blow your mind. The challenges for quantum computing is error correction. So these are resources that are incredibly noisy just by nature. And theoretically, you need significantly more resources to clean up the signal than with the digital equivalents of anything. So that's the main challenge right now, is how do you find utility for these noisy devices that exist today? Because when the equivalent of the regime, when the first transistors or electronic transistors were created, they were very noisy and very hard to manage. Then moving on to cryptography, once quantum computers have hacked a lot of your crypto space, you can replace it with quantum cryptography, or to make your connections quantum secure. The challenge over there is that it's easy to do one-to-one, so it's easy for two people to be quantum secure, but it's very tricky to figure out how to do many-to-many. So if it's a million people trying to securely communicate with each other, for example, like with credit cards, that's a very challenging problem that is not, that is not really been solved yet. And the third major area is sensing. So can we drastically improve measurements, for example, in spectroscopy or metrology? And if you look historically, the largest applications, the largest number, and probably in terms of impact,